So, good afternoon to everybody. The seminar today, the title of the seminar today is Processing of Micro and Nanoparticulate Materials through Compressed CO2 Methodologies. And the speaker is David Piña. David Piña graduated in nanoscience and nanotechnology and with a master's degree in chemical engineering, currently works in a scientific technique service in Instituto de Ciencia de Material de Barcelona, a Spanish public research institution devoted to the study and development of new materials. The soft material service in which David works is mainly focused in the processing and preparation of soft molecular materials through high-pressure fluid methodologies and the characterization on micro and nanoparticulate materials. During his career, David has specialized in the development of materials for biomedical applications, such as nanoparticles or nanoparticles for the smart release and delivery of drugs. He also has high experience in the production and processing of soft materials, such as fine powders of controlled size, aerogels, and microemulsions. So, David, thank you for accepting my invitation. And when you are ready, you can share the screen and start. The floor is yours.
Okay, Sara, and thank you for inviting me and for this opportunity. Can you see my screen?
Yes.
Okay, perfect. I want to apologize beforehand because I'm in an office with more people. So if you hear sounds at any time, please stop me and tell me so I can make them quiet. Okay. Okay, so as I'm gonna lower this. So as Sara told, this talk is gonna be focused on the processing of micro nanoparticles mainly for pharmaceutical applications, but that they are produced with CO2 compressed methodologies. Okay, we're gonna talk about. We're going to talk about molecules that have a therapeutic activity and what challenges do they face. Then we're going to talk about particles, how come particles can improve the state of the technique and the state of the art in terms of drug delivery, let's say, and how can we control the physical chemical properties of these particles. Then we're going to go to supercritical fluid processing. How can supercritical fluids can helps us in the tuning on the characteristics of these particles. And later I'm going to show you some examples of how can we micronize particles using CO2. And finally, we'll see the DELOS-SUSP procedure. This is a process patented and developed here in our Public Research Center for making nanovesicles, and a case of success with these nanovesicles, which is called the nano GLA. First of all, just a brief show of where we are located in the campus of the Autonomous University of Barcelona. It's like 15 kilometers away from Barcelona, but it's very nice because we are out of the city in this very green, kind of like American campus in the movies. It's very chill. I really like it. And specifically, I work in the Institute of Material Science, where, as Sara said, we work with basic research of materials from this to really applied applications of materials. And I specifically work as a technician in the soft service that we produce these soft materials and characterize them. So, okay, let's start with a very brief introduction about molecules that have biomedical interest. Some of these molecules probably are familiar to you. Painkillers, antibiotics, also antitumoral drugs. So in the 20th century, there was an increase in the development, in the synthesis, and in the discovery of this kind of pharmaceutical entities, of these APIs, active pharmaceutical ingredients, they call them. And of course, they have improved the quality of life of so many people, and they have saved tons of life. If we talk about antibiotics and antitumorals. However, these molecules often suffer from poor solubility. and overall bad bioavailability. They have some drawbacks, and this is even more clear when we're dealing with biomolecules that are used as APIs, as active pharmaceutical ingredients, because since they are biomolecules, they are produced inside biological bodies, and they tend to be highly effective and highly selective, and they are not toxic normally. But this doesn't imply that they don't suffer from a lot of drawbacks, such as that they have very poor solubility in the bloodstream. They are easily degraded, which implies that they have very small circulating half-life. And sometimes they have, that depends on the molecule, of course, but they have difficult entering the cells. And as a result of all this problematic, they need multiple dosage. So the idea is, how can we transform, how can we engineer the supramolecular, these molecules into supramolecular entities to improve them? How can we transform them into, for example, microparticles or nanoparticles, or complex them with micro and nanoparticles in order to turn them into efficient drugs? So the use of micro nanoparticles is not only useful for improving the quality of a drug that is already into our bloodstream, but the administration route of some drugs that are going to be administered in solid or powder form is also affected by the physical chemical properties of these nanoparticles, in which that is the form that they are in sometimes. So for example, in this case in here, I present you two images. This may be the very same molecular entity. Both of them might be, I don't know, ibuprofen. So they have the same chemical composition, but they have very different physical chemical properties. I mean, they are both a particulate material with the same composition, but they have very different size or morphology, or they have a different crystalline structure, which leads to different pharmacological activity, okay? Because, for example, the solubility rate of these particles is going to be affected by these physical chemical properties. So once inside your body, in the case of the particles in the right, they're going to be evenly solubilized, while in the case in the left, they're not. And even for inhaled routes of administration, if we are taking like for asthma or something like this, the lungs can only aspire drugs with a defined size and shape. So some of these drugs are going to be effectively aspired, while the others are going to be discarded. So we need to make these particles in order to improve or to effectively deliver some drugs, but we need to control how we make them and the physical properties. So how we do it? How do we control size, polydispersity, morphology, crystalline structure, surface charge? How we do that? Well, we can have like two approaches. The most common or straightforward one, let's say, it's the top-down approach, where we start with a chunk, with a macroscopic solid of a drug, and then we crush it and we grind it into a powder. In this powder, we crush it again until we have particles, micro nanoparticles. Okay, and this is done normally by mechanical methods, such as milling or jet stream or grinding. However, these methodologies, even though they are pretty common in the industry, they have some limitations. First, they cannot create very, very fine powders. You cannot really control the homogeneity of these powders. And also, since these methods normally involve friction, they generate heat, which for biomolecules that can be sensible to temperature, this may be a problem. So we're going to be using another approach, which is the bottom-up way of producing particles, which we start from atoms, well, in our case, let's say molecules with therapeutic activity. And then we're going to build bigger supramolecular entities. And this is done by precipitation or crystallization processes, in which we change the thermodynamic conditions of this molecule that is already dissolved in a solvent, and we make it precipitate. So if we focus on this approach, this precipitation is going to be caused by a supersaturation of the molecule in the solvent. As we said, it's produced by changes in physicochemical conditions, thermodynamic conditions, such as the temperature or the composition. So imagine, for example, that in here, in this vessel or in this reactor or whatever that we have in here, we have a solution of a drug that we want to precipitate. What can we do? We can try to supersaturate the solution, for example, by adding a cooling bath in the sides of the tank, and then decreasing the temperature. As we decrease the temperature, the solubility decreases, so we're gonna supersaturate the solution and we're gonna make the particles precipitate. However, we're gonna do this using stirring, so we're gonna be mixing the solution, but this mixing is not gonna be even in all the tank, and this problem grows larger. We have larger vessels, so it's really not scalable. So in this case, for example, we're probably gonna have the outer parts of the tank that are gonna be cooler than the inside of the tank. And as a result, we're gonna have different profiles of supersaturation across the space. And this is going to lead to different profiles of precipitation. So we're gonna have, such as in the picture in here, different sizes, different shapes, different crystalline structures. Also, the supersaturation can be, as we said, can be produced by change in the composition. And if, for example, we have here a drug that is dissolved in an organic solvent, we can add another solvent, which is, for example, water, assuming that this drug is not soluble in water. So when this water enters in contact with the drug, it's going to precipitate. But again, we have the same problem. The water is not going to be evenly distributed because the stirring cannot be perfect. Ideally, we will have an ideal mixing. Okay, this is something that is taught in chemical engineering, but ideal mixing is really not a reality. So we can get as close as we can, but we're not going to have an evenly distributed pressure, temperature, composition in all the space of our volume. And as I told, as the volume is larger and larger, this is more of a problem. So what can we do? We can try to process these particles with supercritical fluids. So I wanted to make a very short slide of supercritical fluids. Supercritical fluids are a kind of compressed fluids, and they are solvent substances that are above its critical point, its critical pressure and its critical temperature. As a distinctive feature, they have higher diffusivity than liquids. That means that they can more easily and faster diffuse into the substance, like gases. However, its density is higher than for gases. It's more close to a liquid. And the other interesting thing is that close to their critical point, the density can be easily changed with very small changes in pressure and temperature. So by changing a few bars or a few degrees Celsius, you can have a much higher or a much lower density. And with a change in density, it also comes a change in solvent power. Okay. For industrial processes and in industry, one of the most used supercritical fluids is CO2. In here, I'm showing the phase diagram of CO2. You can see here the different phases for different temperatures and pressures. In here, in light blue, we have the supercritical region. So above 7.3 megapascal and 31 degrees, which are very mild conditions, actually, we have already the CO2 in supercritical state. Okay. And even though CO2 has a very bad propaganda, let's say, because it's a greenhouse gas, in reality, CO2 is not toxic, it's not flammable, it's very abundant, and as a result, it's very inexpensive. And since we can turn them into, can turn CO2 into supercritical fluid with mild conditions, it's a very good solvent for processing biomolecules that can be affected by high temperatures. So it's a very good solvent for this kind of processes. So how can we precipitate particles with supercritical CO2? Well, in here I'm showing you again two approaches. Okay, the first one is when the CO2 acts as an anti-solvent. In this case, when the CO2 acts as an anti-solvent, we're going to be able to precipitate particles which are not soluble in supercritical CO2. Okay, if the particles are soluble in CO2, we cannot use this route. In this case, in here, what we have is a drug in a solution, dissolved in an organic solvent, then we want to precipitate. We want to make particles of this drug, and now we have it solubilized into, for example, ethanol, acetone, whatever. And then we're going to pump it into a vessel, and we're going to spray it with a nozzle. So we're going to produce very fine droplets. And at the same time, we're going to pump CO2 in supercritical conditions inside this very vessel. What's going to happen is that the CO2, since it's in supercritical state and therefore its diffusivity is very high, it's going to enter very quickly and very homogeneously into all these droplets. And therefore it's going to be a change in the composition of the droplets, because now it's not going to be only the drug into the solvent, it's going to be the drug dissolved into a mixture of the solvent and the CO2 that has diffused very quickly into these droplets. So if the drug is not soluble in CO2, it's going to precipitate, and it's going to precipitate very fast. And therefore we're going to have particles that we're going to recover into a filter. And the excess of solvent is going to be collected in a vessel, in a collector. On the other hand, this is for when the CO2 acts as an anti-solvent. We have when the CO2 adds a co-solvent, and in this case, it's for substances, molecules, or drugs that are soluble in supercritical CO2. In this case, what we're going to do is we're going to mix the solution of the drug with supercritical CO2 into a tank, and we're going to stir it. In this case, since the drug is soluble in the CO2, it's not going to precipitate. And then we're going to depressurize. We're going to depressurize this mixture of drug, organic solvent, and CO2. And we're going to depressurize it from working pressure, that it's at least above the supercritical conditions of CO2. And we're going to depressurize it until atmospheric pressure. In this depressurization, of course, the CO2 is going to turn into gas, because at atmospheric conditions, CO2 is a gas. And in this gasification, this is a very endothermic process. So the CO2 is going to require a lot of energy to turn from supercritical into gas. And this energy is going to be taken from the temperature of the solution itself. So the solution is going to experience a very sudden and abrupt decrease of the temperature. We're talking about 80 degrees or 100 degrees in 1 second. So it's going to be homogeneously supercooled. And of course, if we decrease the temperature of the solution, the solubility decreases and the particles precipitate. With these procedures in here, in our research group, we have been able to process particles with very narrow size distribution and very small, that we could not achieve with processes that didn't involve supercritical fluids. So we obtained pretty good results with this. Okay, that's for processing microparticles, but what about processing other kinds of particles that are not solid, such as nanovesicles? For this, we have the DELOS-SUSP process, which is a variation of the DELOS process, and that is used for producing these nanovesicles. First, one slide for introducing to you what is a nanovesicle in case you don't know it. Among the different nanocarriers that we have, among the different nanoparticles that we use as nanocarriers, one of them is the nanovesicles. Nanovesicles are vesicles that are in the that goes from 50 to 200 nanometers, more or less. And what a vesicle is an spheric-like structure that is formed by a bilayer of amphiphilic molecules. In a way that if these vesicles are in an aqueous phase, the polar heads of these amphiphilic molecules is going to be exposed to the water, also in the outer part, in the inner part of the vesicle, and the apolar parts of the amphiphilic molecules they're going to be packed together, forming the inner membrane. And these nanovesicles has a very good function as drug delivery systems because they can protect the drug from degradation that can occur inside our bodies. If these drugs are hydrophobic, these nanovesicles help us solubilize them because they can include them inside the membrane. Also, they can promote membrane fusion and they can be functionalized. That means that they can be, like, let's say, decorated with ligands that can recognize some receptors inside our body, increasing the specificity in case they are loaded with a drug. Now we come back to the DELOS-SUSP process. So the DELOS-SUSP process, it's similar to the DELOS process that we explained a couple of slides before. In here, we're going to load our vessel with a mixture, solution of the membrane components of our vesicles in an organic solvent. And also, if we can add in here hydrophobic actives, so molecules that have therapeutic activity, we can also include them in this step. Then we're going to produce an expansion with CO2. We're going to pressurize everything with supercritical CO2 until it is homogeneous, and then we're going to depressurize it. But as opposite as in the DELOS process, in here we're going to depressurize it in a jet stream of water or an aqueous phase instead of a filter. And this aqueous phase can have or may not have hydrophilic actives. And this is going to produce nanovesicles that are already loaded with the molecules that interest us. And this is very interesting because it's one-step process. You don't have to generate the vesicles and then you have to load them with the drugs. So it's a one-step process that can achieve very homogeneous systems, such as the ones that you see here in the left. Okay, it can generate small unilamellar vesicles that are the vesicles that are often required for this kind of pharmacological applications. And we're still studying this process. It's true that we are not completely sure why the procedure yields vesicles with this very high homogeneity, but we know it's related with the cooling produced by the depressurization. Okay, because we have tried without similar processes without the cooling, and it doesn't occur. We obtain what we obtain with other conventional methods for producing vesicles, such as thin film hydration, where you obtain bigger vesicles or multilamellar or more heterogeneous vesicles. And for pharmacological applications, these vesicles often need to be post-processed through sonication extraction or other methodologies to obtain the homogeneous systems. So it's more steps, more money. Okay, so this is all for the DELOS-SUSP process. And now to finish this presentation, because yes, I'm in time, I think. I just wanted to show you a case of success of some nanovesicles that we obtained through the DELOS-SUSP process. let me explain you first a very brief explanation about the Fabry disease, which is a lysosomal storage disorder, in which the patients that have these rare conditions lack the alpha-galactosidase enzyme, and this produces this controlled accumulation of glycosphingolipids inside the lysosomes of some organs. So let's say that this organellus, that is the lysosome, it gets filled with fats, and this leads to dysfunctional organ and early death. Okay, there are currently some treatments which are enzyme replacement therapy, where for these people that does not generate naturally, let's say, this alpha-galactosidase enzyme, you can inject it. Okay, but as we said in the introduction, this enzyme has a very rapid degradation. It's very immunogenic, and it has a very poor circulation and half-life in our body. So it requires large doses in order to work properly. And as it requires large doses, it's a very expensive treatment. So from ICMAB, we joined an European project coupled with a lot of interdisciplinary academic institutions and also companies, where it was where the aim was to generate a novel nanoliposome formulation to include this enzyme and improve the already treatments that are in the market, such as the Replagal and the Fabrazyme. This was a success because we could, after these 3 years, we managed to formulate through the DELOS-SUSP process with supercritical fluids some vesicles that were form of DPPC and rich in cholesterol. And we could load inside the vesicle this alpha-galactosidase enzyme that is necessary for these patients. And we could also functionalize these liposomes with cholesterol RGD, which is a ligand that facilitates the cellular uptake through the integrin receptors that are in the cells. Okay, in this with this product that is already in preclinical state, we could obtain so in the in vivo studies that we made, they showed a higher efficiency than the already commercialized products. At least for some organs, for kidney, for brain, and for heart, I think. So yes, we could improve the current treatments that are in the market. That is all. I just wanted to leave you some key points, some reminders for you to take home. So the physicochemical properties of drug compounds take into account that they impact very highly in the pharmacological properties. The chemical entity is what has the therapeutic activity, but how we present this chemical entity to the body is also very important, because if this molecule can treat us from a disease but it's not soluble in our bloodstream, then it's not good. Okay, also controlling physicochemical properties is not an easy task, and I have to say that from my experience with different companies, is easily overlooked by companies that produce these APIs, these ingredients, and then they get frustrated because this APIs doesn't reach higher levels of clinical studies. And in this way, we could use supercritical fluids to overcome the limitations associated with engineer the supramolecular structure of these substances. And as a last key point, well, I have shown you a nanovesicular system that is produced with supercritical CO2 methodologies that has successfully achieved to improve the efficacy of an already established drug product. So that was it. I wanted to acknowledge my team and also the financial support of these different entities, and acknowledge the work of Nora Ventosa and also Elizabeth Gonzalez and Judith Thompson, that they perform all the studies for the nano GLA that I just showed you, and also all the nanomolvia research group and the nanotechnologies spin-off that they have made also a very good job in escalating this technology. Well, are in the process of escalating this technology. That's all. Thank you. And if you have any questions, I will be happy to try to solve them.
Thank you, David, for your very interesting and clear presentation. So as you told, now it's time for questions. I remember you that if you want, you can just ask or write in the chat and I can read for you. I think we have one in the chat from Elena. So, good afternoon and thank you for your interesting seminar. I have a curiosity. What's the advantage of preparing liposomes with the DELOS-SUSP technique?
Yeah, well, as I was explaining before, so there are a lot of methodologies for producing liposomes. Most of them are variations of thin film. Well, I mean, not most of them, but some of them are variations of thin film procedures in where you dissolve the membrane components in a solvent, and then you evaporate the solvent, and then you rehydrate, and they form these vesicles. But they normally yield pure homogeneity systems, and they have to be post-processed. Also, the DELOS-SUSP, due to the nature of the process, it's easily scalable. It can be produced in a continuous mode, while some other techniques are more related to batch mode. And it's more difficult to escalate them. And finally, I have to say that the use of CO2 substitutes in part the use of, so you can substitute the use of conventional organic solvents, which are more toxic, while CO2 is not toxic.
Okay, fine. So, are there more questions, curiosities? Don't be shy. Well, in the meantime, I have some curiosities, like more technical, maybe. You mentioned the scalability. So,
Yes.
is it possible? And well, it's expensive. So, tell us something about also the applicability of this methodology.
Yes. So regarding the DELOS-SUSP process, yeah, it's scalable, and yes, it's expensive. So it's expensive because the equipment that we used. So the bad part of this process is that all the equipment has to be thought for high pressure, and of course, high pressure means certifications, means there are bigger walls, and high quality stainless steel, and this equipment is very expensive normally. But once you have it installed, so once you have built your plant, let's say, the operation cost is not very high because CO2 is very cheap, and also since all the vesicles are being formed in the joint for the DELOS-SUSP in this part in here, where we join the two fluids. This can be made in continuous. We can feed all the time the reactor with so we can produce a continuous stream of the pressurized organic expanded solution. We can join it with a continuous stream of water. So since it can be made in continuous, it can be easily scaled, and this is something that our colleagues from Nanomol Technologies spin-off are now working on it.
Okay, thank you. And so it's also, maybe I imagine, quite dangerous equipment. So probably to manage the equipment is required like a specific technical training.
Yes, well, I mean, these things are very looked. we have a lot of safety measurements. We have burst discs. We have valves that release the pressure if the pressure goes out of control. So of course there is a lot of safety measures, but yes, you have to be ready to, you have to be trained to work with this, because as always, if you're working with high pressures, I remember in here we're working with 73 with 100 bar, and if I recall correctly, above 2 bar, it can already break your eye. So yes, we're much above. So of course you have to work with the safety measurements and so on. Yes.
Well, but besides all this stuff, we know that it's a very versatile technique, so there is a lot of possible applications.
Yes.
Fine, it's fine. It's very interesting, really.
Thank you.
So, are there more curiosities, more questions? Well, if not, I want to thank you again for participating, for accepting my invitation, and we will, I just tell you some information. Next week, next Thursday, we will have a biology seminar. We will let you know the information soon in the website. So thank you again, David, and
Thank you, Sara.
see you next Thursday.
Goodbye. Thank you everyone for
Bye.
attending.
Bye.